I'm going to give the first talk. Yeah, so this work is lifting linear sketches, optimal bounds, and adversarial robustness. Joined with Elena, who's here, Honghao, who's here, Huacheng, and Samson, who is here. So you've already seen the streaming model in earlier talks. There's an underlying frequency vector x. Think of each of the coordinates of x as indicating the number of occurrences of some item. And you see a stream of items, A1 through AN. When you see an occurrence of, say, the tth item AT, then you update your frequency vector XAT. Its new value is the old value plus 1. At the end of the stream, you want to evaluate or approximate some function f of this underlying vector x. And one of the main goals is to use memory, which is sublinear in the dimension of the input vector x, as well as the length m of the stream. Okay, so there are many functions that are studied in this model. Edith talked about a lot of them earlier this morning. So L0 estimation, which is the number of coordinates I for which xi is not equal to 0, the support size. LP estimation, so when p is 2, this is just the Euclidean norm. And heavy hitters, finding those items which have large frequency. So maybe the frequency of the ith item is at least epsilon times the Euclidean norm of the underlying vector, and so on. And x doesn't need to, we don't need to look at these statistical problems. X could be represent the entries of a matrix, the edges in a graph, and so on. Yeah, so here is a stream, which here's the underlying frequency vector. You see that item 1 occurs 3 times, so there's a 3 here, and this has 4 distinct elements. A more general streaming model is when you allow not only insertions of items, but insertions and deletions or arbitrary changes to additive changes to this underlying frequency vector x. So again, you have x, which is initialized to all zeros. Each iteration, you change some coordinates, say the atth coordinate of x, by adding some amount wt to it. Okay, so the stream consists of pairs, which are coordinate together with the change in value. Yeah, so before wt was positive, now it can be positive or negative. And one of the most common algorithmic techniques we have for insertion deletion streams is that of a linear sketch. So the idea is for the algorithm to maintain A times X for matrix A throughout the stream. So this matrix A, you should think of it as wide and fat. It's doing dimensionality reduction from this n dimensions of X to a much smaller number of dimensions, the number of rows of A. In the streaming model, the entries of A typically are poly-n bounded, so you can represent the entries of AX efficiently. And the matrix A is typically represented pseudo-randomly, perhaps with a hash function that's easy to specify. Yeah, and the reason for using linear sketches is it's very easy to maintain under additive updates to the coordinates of X. So if you have some change, delta t, to the underlying vector X, then, without knowing X, you can update your sketch. So you can add A times delta t to A times X. Okay, and at the end of the stream, the algorithm has maintained some sketch, A times X, and it outputs some function, G of AX. Okay. Yeah, so why are we looking at linear sketches? Well, it turns out that for almost all known problems, the best algorithms we have in insertion deletion streams are linear sketches. There's some evidence that for sufficiently long streams, the optimal algorithm in an insertion deletion stream might as well be a linear sketch. Okay. Yeah, so this conjecture in general is open. It comes with some caveats. There's a mod p version of this conjecture, which is true for small streams. Even for small streams. In general, we don't have a proof of this, but we have a lot of evidence that the optimal algorithms should be linear sketches. Okay, so we want to understand lower bounds on linear sketches. For a given task, how many rows does your sketch A need to have to solve some problem? Right, this is lower bounds are fundamental to our understanding the hardness of streaming problems. what is a popular way of proving lower bounds? Well, we can define hard distributions, say D1 and D2, that exhibit a desired gap for some problem of interest. So the algorithm needs to tell if the input came from D1 or D2. And what we try to show is then that, say, the variation distance between the image of a sample X from D1 under the sketch A with the image of a sample Y from D2 under A is small. Okay, so if the number of rows in your sketching matrix A, that number R is small. Okay. So here's a simple example. Let's suppose I wanted to prove a lower bound for estimating the Euclidean norm of a vector X using sketching. I can define my two distributions to be, one is just an isotropic normal distribution, so mean zero identity covariance. And the other distribution is again normal with mean zero, but variance 1 plus epsilon times the identity. Okay, if I take a sample from this, its squared Euclidean norm will be very close to n, and here it would be very close to 1 plus epsilon times n. So I need to figure out, if I want a 1 plus epsilon approximation to Euclidean norm, I need to figure out which one it came from. Okay, here's a nice simplification that you can do. If I'm going to sketch an input with the matrix A, I might as well assume that the rows of A are orthonormal. Why? Because I'm maintaining A times X, and I can always do a post-processing which changes the basis for the row space of A. Okay, I can always multiply it by some R by R matrix at the end to change the basis. So I might as well assume A has orthonormal rows. Why does that help? Well, then it's very easy to say what the image of one of these vectors is after applying the matrix A. If X is drawn from a standard Gaussian, then A times X is also drawn from a standard Gaussian. A has orthonormal rows. The dimension of the Gaussian now is R instead of N. Similarly, if Y was drawn from this other distribution, then the image A times Y would be Gaussian with variance 1 plus epsilon times the identity in R dimensions. And so now you're just asking the question, how large does R need to be so that if I get a sample from this, you can think of having R samples from this distribution versus R samples from this distribution. How large does R need to be to distinguish the two distributions? And then you can use standard bounds, the number of samples to distinguish normal distributions. You can prove this using Hellinger distance, or this is standard, so you can show that R needs to be at least log 1 over delta over epsilon squared to have a failure probability of delta of distinguishing these. Okay, so this R, remember, is the number of rows of your sketching matrix, and this lower bound is resolved. Okay. Question, yeah.
Choose an upper bound on the size of the bound?
No, so this was just a lower bound that works for any linear sketch. Yeah. Okay. So these techniques imply lower bounds for lots of problems. LP estimation more generally, compressed sensing, when your input describes the entries of a matrix, eigenvalue estimation, just testing if there is a negative eigenvalue, finding the maximum eigenvalue. A chi-fan norm is the sum of the top few eigenvalues. And one topic tied to this workshop is norm estimation for adversarially robust streaming. Okay, so as Edith mentioned in earlier work with Moritz Hart, we do have an attack that can break any linear sketch. I'll get back to that later in the talk. Okay. And yeah, to prove these lower bounds, the distributions D1 and D2 are often chosen to be multivariate Gaussian or somewhat near Gaussian, maybe Gaussian plus a nice discrete distribution. Because then you can say, oh, my sketching matrix is orthonormal, and you can use all these nice properties. The proofs are very simple. So the problem is that these lower bounds, they require the entries of the input vector X to be real valued as well. Right? Our distributions were, X is drawn from a Gaussian. And since going back to Guy's question, since we're proving lower bound against arbitrary sketches, this is inherent, right? If X had finite bit complexity, I could choose my entries in A to have large enough precision to sort of recover X from A times X. Yeah, but the stream model is defined on a stream of additive updates to X with finite precision. So you should think of X as having entries that are, say, polynomially bounded integers. And your matrix A, as I said earlier, in a stream should also have polynomially bounded entries so that you can store A times X efficiently. And so these issues mean that actually none of the above lower bounds for all these problems actually apply to the data stream model. Okay, so because of this, most discrete lower bounds were instead obtained via other approaches. For example, communication complexity is a standard way of proving lower bounds. In particular, one-way communication complexity for data stream problems where you often only have one pass over the stream. But there are many open questions in communication complexity, very basic seemingly open questions. For example, suppose you have two players, Alice and Bob, that each have a D by D binary matrix, okay, A and B respectively. And Alice wants to send Bob a message so that Bob can approximate the operator norm of the matrix A plus B, okay, the max singular value, say up to a constant factor. Then there's a trivial D squared upper bound, right? These are binary matrices. Alice just sends the matrix to Bob. But we don't have any really interesting lower bound. Okay, the best lower bound is omega D, which follows from a simple reduction from the set shortness problem. Doesn't matter. My point here is that this is a communication problem for which there's a gap. However, you can prove if the sketching dimension of this problem, where you think of A and B as these are matrices that have been vectorized and you sketch them, you can prove that you need omega D squared sketching dimension to approximate the operator norm of a matrix up to a constant factor. Okay, so here's this big gap. Like in the data stream, what is the complexity, the memory complexity of approximating the operator norm up to a constant factor, right? Sketching, we have this. Data stream, we have a much weaker bound. So can we somehow obtain discrete linear sketch lower bounds, which would be useful for streaming? And so one idea is we could try to discretize the input distribution that is hard for continuous linear sketches. But it's not clear if this will work. If I take these Gaussians and I truncate the lower order bits, I destroy rotational invariance, and it's not clear how to prove anything. So it's not clear that information about the input is not revealed by truncating these lower order bits. Because you're applying the sketch to this, okay? It's not like you're taking the output and truncating. You're taking the input and truncating. So question, is it possible to lift all of these many linear sketch lower bounds that we have for continuous inputs to obtain the same linear sketch lower bounds for discrete inputs? Okay, that's one question. And related to this is the adversarially robust streaming model, which you guys have seen a lot of talks on this. So just very briefly, I think you've even seen these slides from Samson yesterday. So yeah, you have these updates to some underlying vector X, and you have this attacker that's generated the stream, right? So the attacker says, here's the first stream update, and here's the algorithm that says, the answer is 1. Maybe it's estimating the support size of the underlying vector X. And the attacker, looks at the answer and says, okay, here's the next stream update. X2 goes to X2 plus 1. What's your answer now? The algorithm says, oh, my answer is 2. Okay, all right. And the attacker keeps going and, makes another query. Algorithm gets it right, makes another query. And here the support size is still 3 because it's updating 1 again. But maybe the algorithm says the answer is 4. The algorithm is fooled. And so the attacker wins. Okay, so that's the game here, which is that the attacker is generating the stream at each update. It's observing the output of the streaming algorithm, just the output. It's this black box model. And it's choosing the next stream update based on everything it's seen so far. Its goal is to break the streaming algorithm. Okay. So what do we know about adversarially robust streaming? So in this insertion-only model, where there are no deletions, there's a lot of for all these classical problems I mentioned, there are a lot of very tight bounds, really tight bounds in terms of the accuracy epsilon and the log factors. You don't need to digest this. But these are just a number of problems that we discussed earlier. And the point of this slide is that if you look at the next slide, we can get roughly the same bounds in the robust case for insertion-only streams. Okay, so the epsilon dependence for all these problems is the same. So these are problems like support size estimation, norm estimation, heavy hitters, and no losses are necessary, with the caveat that some logarithmic factors are lost. Yeah.
So for the statistical distance technique you mentioned, is that anything special to like adversarial robustness, or because it's some
No, that was just an example of how to prove a sketching lower bound. Yeah. Okay, so yeah, so the sort of the reason these are in the same talk is because the techniques used to lift we're going to lift sketching lower bounds in the continuous case to the discrete case, and I mentioned there's this attack for sketching lower bounds in the continuous case, and that's also going to be lifted to the discrete case. Yeah. Okay. So for what about insertion deletion streams? So for adversarially robust LP estimation, you can use differential privacy techniques that were discussed here. So linear sketch with R rows is robust to R squared queries. You can think of each stream update as providing a new query. There are also algorithms with space sublinear in the stream length M. So Shistov has some, and Omri, yeah. So what this means is the updates in the stream are, say, +1, -1, or they're very small. Sort of, you kind of use the fact that the updates are very small at a time. But you can get some slightly sublinear stream length algorithms here. For polyN queries, there isn't a known algorithm for general LP estimation with constant factor approximation in sublinear space. Okay, now what about the continuous case? So there is an attack on linear sketches that I mentioned. So a linear sketch for LP estimation, p greater than 0, is not robust to an adversarial attack. In particular, you can break a sketch with R rows with poly R queries. So yeah, you need omega n space to be adversarially robust. So this is an old work with Hart. The way this roughly works is the algorithm tries to learn the row span of this sketching matrix A. Okay, so the idea is the attacker is going to generate a bunch of Gaussian queries to the sketch, but it's going to generate a bunch of queries that say variance, which is standard identity, then 1 plus epsilon. So sorry, this identity, then 1 plus epsilon times the identity, then maybe 1 plus 2 epsilon times the identity, and so on. So it generates all these Gaussian vectors of different norm, and these are fed into the sketch, and the sketch can't really tell, like, it's going to look at its output. Since the input was a Gaussian, its output AX is characterized really just by its norm. The direction doesn't mean anything. And it can't really tell, it looks at the norm of its output AX, and it can't really tell if the norm is a little bit higher just because you happen to choose a query which was slightly more aligned with the row span than it should have been. Or if it was the case because your input had a slightly higher variance, right? Because I said the algorithm, it's choosing the variance at random as well. So it can't really distinguish those cases, and because it can't distinguish those cases, it leaks information about which rows, which queries are correlated with its row span, and can roughly, slowly, and adaptively reconstruct the row span in this way, or break the algorithm at some point along the way. Okay, that's just very high level, but the point I want to get across here is the attack randomly generates Gaussian vectors. The analysis critically uses rotational invariance of Gaussians, and so again, just like the earlier linear sketch lower bounds in the non-robust case I mentioned, this attack only works on real valued inputs. Okay, one other thing is that it actually only works against LP estimation for p greater than 0. So it doesn't handle the support size estimation problem when p is 0. Recently, and you'll see Honghao's talk later today, with the same authors, we resolved the robustness of L0 estimation in a finite precision stream using discrete linear sketches. But the techniques there are very specific to L0. And the second question I want to ask here is, does there exist a sublinear space adversarially robust LP estimation linear sketch in a finite precision string? Okay, I think this is the right question to ask in the sense that the previous attack really needs continuous inputs, and so doesn't really say anything. Questions? Okay, so we give a general technique for lifting linear sketch lower bounds for continuous inputs to achieve linear sketch lower bounds for discrete inputs, and thus answering both of the previous open questions. Okay, so we get this new set of lower bounds for non-robust algorithms, and we also lift this attack in the continuous case for robust algorithms to discrete sketches. So, okay, I'll start, just to say the results, the result, let me introduce some notation. So the techniques in this paper use lattice theory, and Elena, who's following, giving the second part of this talk, is going to describe more about the techniques. So let D0 S transpose S be the discrete Gaussian distribution. It's supported on all integer vectors. It has mean 0. In fact, yeah, all the distributions we'll consider have mean 0. And the covariance is S transpose S. The probability mass function is just the same as the continuous Gaussian density function at integer lattice points, okay? So probability x equals x is e to the minus x transpose divided by twice the covariance times x. And and there's some normalizing constant here. This distribution is not very nice. Doesn't have anything like rotational invariance, but it's discrete. And the hope is maybe we can somehow use these to prove our lower bounds. And here is our main result that we apply to a number of problems. So suppose X is a discrete Gaussian, mean 0 and some covariance matrix. And Y is a continuous Gaussian, mean 0, the same covariance matrix. And let Z be an arbitrary integer distribution. Suppose you have some function f, which has the following property. The probability over an x drawn from this discrete distribution, capital X plus Z, and a y drawn from this continuous distribution, which is capital Y plus Z, the probability that f of x does not equal f of y is small. Okay, you can think of this f as maybe, is the norm at most something. Okay, so maybe f is a binary, indicator function. And suppose you have a good post-processing function g, which takes your discrete linear sketch ax, so x is discrete, and g of ax equals the function value when x is drawn from this discrete distribution with good probability. Okay, you just have a good streaming algorithm, g. Since you're in the streaming setting, we want our sketching matrix A to have polynomially bounded integer entries. And suppose that your two distributions, the covariance matrix S transpose S has all singular values which are large enough poly n. Okay, we're proving lower bounds. We can choose whatever covariance matrix we want. This is not an assumption. Then here is the punchline. There's another sketching matrix, A prime, which has slightly more rows than A. Instead of R rows, it has 4R rows. It's real valued. There's some corresponding reconstruction function h, such that if I apply A prime to this continuous input y, then h of A prime y is f of y with good probability. And here y is coming from the continuous distribution, capital Y plus Z. Okay, so the idea here is, hey, if I have a good sketching algorithm for discrete inputs, then I can also get a good sketching algorithm for continuous inputs. The new sketch has the same number of rows up to a constant factor as the old sketch. So if I can prove a lower bound on the number of rows of the continuous sketch, then I inherit that lower bound with the corresponding discrete sketching. Okay, let me show it to you in action, and then soon let Elena take over. So here's this L2 estimation problem that I talked about earlier. Let's let, we want to get a discrete lower bound. I already showed you how to prove a continuous lower bound. So let the function f be 0 if the norm of x is, say, at most 1 plus epsilon times some parameter capital N. And it's 1 if the norm of x is at least 1 plus 3 epsilon times capital N, and you don't care otherwise. Okay, so here's a general recipe for proving lower bounds. Let's let x1 be a discrete Gaussian where the covariance is n squared times the standard times the identity. And x2 is a discrete Gaussian where the covariance is 1 plus order epsilon times n squared times the identity. Okay, we define the corresponding continuous distributions y1 and y2. Okay, I just replaced d with n. Everything else is the same. Now, f satisfies the following property. If I draw a sample from this discrete Gaussian versus this continuous Gaussian, they're going to fall into the same, they're going to have roughly the same norm. Okay, so the function f is going to be the same on a sample from here as from here, right? The squared norm is going to be roughly n squared. Yeah, so on the other hand, if I draw a sample from here versus a sample from here, yes, the squared norm will be roughly n squared, and so the norm will be at most, say, 1 plus epsilon n. F of x will be 0 in this case. F of x and f of y will be 0. In this case, f of x and f of y will both be about 1 plus order epsilon. Okay, so it satisfies this problem. Okay. So how do we apply that template? Suppose there exists a good streaming algorithm. So A is a discrete sketch that can distinguish x1 from x2 and has R rows. Okay, it has to distinguish x1 from x2 because these have very different norm. Okay, if it's a good L2 estimation algorithm. From our theorem, there exists a good continuous algorithm with sketch A prime, which has 4 R rows. And it can distinguish a sample drawn from y1 versus y2, these two continuous distributions. But we just saw how to prove a lower bound for the continuous case. We said any any algorithm in the continuous case for these two continuous distributions y1 and y2 requires the number of rows to be at least log 1 over delta over epsilon squared. Therefore, 4R is at least this, which means our original sketching dimension over the integers is at least this. Okay, so that's the whole proof. Any questions about that? It's a simple example. And using this this general theorem, we're able to lift a lot of lower bounds that we had in the continuous case. We had previous discrete lower bounds, and here are the new discrete lower bounds. And these new discrete lower bounds just match what we had in the continuous case. So for problems like estimating the operator norm, I said that there's this communication problem that's unresolved. The previous discrete lower bound was roughly d, but the continuous lower bound was roughly d squared, and we get that same d squared lower bound in a discrete streaming setting, and so on. Okay, so for adversarial robustness, as I said, the attack on there's an attack in the continuous case. We can't directly apply this general theorem to lift that to the discrete case because the attack is adaptive. There's sort of multiple rounds of adaptivity, but if you open up the procedure and the analysis in the earlier work and use this lifting technique in the right places, then you can now get a poly R log n query attack in the discrete case. Okay, so there's no adversarially robust discrete sketch either for L2 estimation. More precisely, for any LP and for any accuracy roughly. So if B is any approximation factor, for any integer sketch with R rows, there's an algorithm that can find, the attacker that can find an integer value vector on which the sketch fails to output a B approximation to the LP norm. So for any constant B, the attack uses poly R log n adaptive queries and R rounds of adaptivity. Okay. So I think this is a good time for me to stop. Are there any questions about the results? Yeah.
So this transformation, is it computationally efficient? I know you don't care about it, but it must not be, right?
You're going to see the transformation, so Elena's going to talk about it.
Because here, you're solving this shortest integer solution problem, right? Kind of. You're breaking an integer sketch using an integer. So you're finding for a I guess based on the continuous paper, right? You're finding a vector in the kernel, essentially.
That's right. So you can imagine it's not really in the kernel. It's something that like shrinks a lot.
Sure. Yeah.
That's right. So there is this short integer sketch problem that's hard. One thing is that this is over the integers. That problem is typically over finite.
Okay, so that makes sense.
You'll see the attack clearly. Yeah.
Okay.
Okay. Yeah. Any other questions? Yeah,
It's like the lower bounds that you're able to live if you based on this Gaussian gate hard case.
Yeah, so so the theorem I presented is definitely of that form.
Yeah, I mean,
Yeah, if you have, I mean, I guess like all of these lower bounds were done with Gaussians. If you had some other continuous distribution, yeah, I'm not sure. We don't have the general theorem for such distributions. But this is enough for everything that all those examples I said, as long as you choose Z appropriately. So typically it could be like a Gaussian plus a spike, for example, is the hardness for moment estimation, and heavy hitters for p greater than 2. It's also a hard distribution for a max eigenvalue because you take a Gaussian matrix and then you add a random rank 1 matrix. So that can be discrete. But yeah, if you have some completely different continuous distribution, no Gaussian component, then I'm not sure. Any other questions? Okay, yeah, thanks.